small one. As you can see, the mu is kind of around 0, and the sigma here is around 2. The variance is around 2, and then that is the probability per sample in that data set. So you can do that per data set, and if you have kind of done that, we can go to the next step, which means the thing is here, yes, I said that you can just use a standard deviation, but if you can see, we have a probability here, which the probability is the representation of the likelihood of that sample in your data. So you can just use that probability here and use a threshold for that. So you can say if the probability of each sample is maybe lower than I don't know, 0 point maybe 1, then that's anomaly. Then this one will be anomaly here. So you can just use the probability. Here in those data sets, we want to use that p, which was the probability per sample or the likelihood per sample, to say if something is anomaly or not. Which here you can see that this is the norm and this is the probability, and then we can visualize that. We can just say, okay, now I know what is the probability, and then I can have a threshold. I can play with that threshold. I can use different number here, and then given different number, I will have different point as anomaly. So if I just use p equal to b, so if I want to p be 0, if I say if the probability of that sample is less than 0.001, if I visualize that, then I will end up with something like that.
So then the result of that multivariate Gaussian is just the p-value for the data point, right?
Yes. Probability, yes.
Okay.
Is it the likelihood?
Yes, exactly, actually.
A question, I got confused, maybe it is a notation issue, maybe not. So standard deviation is sigma, variance is sigma squared.
Yeah.
Yes. Yes.
So I think somewhere you take square root of sigma, meaning that sigma actually denotes variance.
Yeah, I should have said that variance instead of sigma.
But it depends, because like if it's multivariate, sigma is just a variance. So the standard deviation is the square root of sigma.
Naming, you can the output of that function is variance. If you want to compute the standard deviation, you have to square it. But variance is sigma squared, and the sigma would be a standard deviation. You're right.
Statisticians are wrong. Because in linear algebra, sigma is a singular value, which is standard deviation.
No,
They overloaded the sigma. That's all.
Overloaded, that's the right word.
That's a mistake. I'm late. Second.
So are you doing a task now?
Yes. So that's for visualization. I don't know. You can just use that code, or should I can copy that code to the stack or somewhere. Amir, how can I transfer this code to them? Because that was part of the exercise. If I want them to actually use the code, or
So you can give them the full notebook after the session, right?
okay, how about now? If I want them to use that visualization,
Oh,
maybe
you can just copy the file to the
Okay.
students folder,
okay.
because you have a separate file, right?
Yes.
Or I'll ask Willie to do that in continue.
Okay. I was like, the thing is, here is just for the normal one, but you want to see how just having one, just using the Gaussian model can fit to the different files, so you can just play with it. I can do that here for you so you can see, but I wanted you to actually play with it. Use different threshold and see what's going to happen. I mean, I can do that, you can see, or you want to do it yourself, which one you prefer.
They want to do it themselves, obviously.
Then, okay. I can choose.
There was the silence of confusion.
Unless you answer, I'm going to answer for you. That's how it works.
Yeah, because okay. I was trying to do most of the scene, and then I was like, okay, some of the scene should be exercise, so you will be forced to play with it, to learn it, and then we can kind of work in the same pace, so everyone on the same page. If is there any question, you all can raise. So that's why these cells are hidden, and then maybe to go forward, I can share, so step by step we can fill it.
So do you want to give them about 15 minutes to figure this part out, and Willie will copy the file? So if they need help, they can copy paste from that file.
Sure.
Yeah?
Yeah.
Okay.
They won't need, maybe 5 minutes should be enough.
Do you want to repeat the task so that online people also know what they're doing?
I guess they should know. It's like just fitting a Gaussian, just by computing the probability using these two functions that we defined at the very top, using the estimation of Gaussian, and then using the other function to get the probability for all those synthetic data. And then you should be able to plot it and see, based on your threshold, what is there, what is not.
Anyone want coffee to help their brain work? Yes? Yeah, help yourself. Yeah.
I'll get something for you.
I'll boil some hot water.
Is everyone ready to go online? All right. Whenever you're ready, here. Okay. Go log your line.
Okay. I just wanna paste some of this code here.
Just like wash the cups when you're done. Whoever signed up for coffee. If you didn't sign up, there is coffee, but it's cold and you have to microwave it, which is what I do in the whole company.
Who wants? Do you want? Or you have enough coffee? Or no, you're on to your second?
Do you want to start?
Sure. Okay. So if you have, let's say, normal distribution in each dimension, as you can see, just by having just by fitting one normal distribution here to a Gaussian model here, you should be able to capture most of the anomaly. And by changing the threshold, you can actually say what is your threshold of finding an anomaly. And I should have my copy as well for okay, we have a copy here. So there is two things here that I want to try that you can try as well. First one is a Gaussian, but the likelihood is a number. Then from that moment, that number is the one that will say what is normal, what is not, and you should kind of have that number in your mind. So, and it is like, remember when you were using 2 standard deviation or 3 times the standard deviation was like your threshold of saying that what is normal, what is not. Here you can just use the probability, and if I just use that number, that will be the anomaly for me. But let's say if I increase that number or make it to be smaller, what will be the effect of that number? So maybe we are getting closer, and then let's even make it a bit bigger. So you're getting closer to the core.
So this threshold represents what's the percentage that you include the data, right?
Yes. So not a percentage, but is they call it likelihood. Is like based on the, okay, you can convert it to percentage as well. That's why some of the model they have like they call it like an inflation percentage. So they're doing that something like that for you. So it means here you can compute all the point. You can say how many sample here has been categorized as anomaly. How many number do you have in your sample? Then by computing the ratio, you can say what was the percentage of anomaly in your data. And if you have something in your mind, if you say that my assumption is 1% of the data should be or will be anomaly, then you can play with the P in a way that just 1% of the data is anomaly. So see, if I increase the P here, more data will be like detected as anomaly. And if I decrease it, then maybe my threshold is super higher. So I'm just saying that you should be too far from my main distribution to call you anomaly. So it means it's kind of like your threshold, your like it is like based on the based on your assumption of the data. Like what do you mean by saying something is fraud? And even if I increase it even further. Just want to make sure that not that many samples are here as fraud. So see, I can just make it even to, if I believe that the number of fraud is super small, I can just actually make it to be small. And then the number is not just that many numbers, it's super few. So as I said, this can be said. Remember about the just computing the standard deviation in just an area number? I said is important if you have anomaly in your data or not. If you have, then you have to set the threshold based on that. So it means your assumption is, okay, I know 1% of the data is anomaly. Then based on that assumption, you're assigning what will be the threshold of variance or what will be the threshold of the probability here. You have a question? Okay.
No. Yes, I do. So in statistical modeling of the sort that I was originally trained in, you would often Winsorize your data because you get rid of the extremes, but presumably if it really is a parametric distribution generated by a parametric process, then the data on the end shouldn't really be changing the variance that generated it, right? So you don't need to drop data by its distance in this way. In principle, if you rotated the dimensions so that they're aligned to whatever in particular, and you could go and Winsorize your data, right? Wouldn't this make sense?
Kinda. So you see, okay, the thing that you're saying, or maybe you can say it, is like whenever you're fitting any kind of model, you have an assumption, and maybe here assumption is, okay, I'm going to fit a Gaussian, but
Here you're using the variance to drop the most extreme
variant
things.
Because assumption is the data is normal.
But those things are controlling the variance. Their presence is controlling the variance.
Yes.
So the alternative is the Winsorization, which means I'm just going to drop the 5% most extreme.
And then recomputing the variance again?
Well, then you just do everything as per normal without that data. But presumably that tail data is the same as the internal data. the data closer to the central tendency. So it shouldn't matter if it's not anomalous or strange, right? And in this way, you don't kind of pollute your dispersion. Does it make sense?
Yes, but the problem here is like that.
You have to rotate it.
Here, like here, for sure, all these points that has been marked as anomaly, you can say yes, they are anomaly. But if I lower this number, even maybe more, and if I say, no, that's my tail, which one is the correct one? Which one should I remove? Which one should? You see, it is like one of the things that I said they're using in machine learning is by cleaning data. By cleaning data, it means they wanted to find all those things that they're maybe far from your core of the data, the main distribution of data, and then maybe they're just removing them to make sure that after that moment the data is super clean, or the distribution is better, or they can come up with a better Gaussian fitted on the data. By rotation, I don't know what you exactly mean here.
Well, I mean in the sense of if you don't necessarily, so in a multi-dimensional problem, you can't just Windsorize. That doesn't make sense. You can't say I'm going to reject the 5% most extreme data on both sides.
Yes.
So you need to, and in principle, because it's multivariate, you don't really know how it's aligned in the space. It could be inappropriately aligned, but once you align the data, then you can go and remove off of each dimension the appropriate size as per your approach. Does it make sense? That's why you need to rotate it.
You mean you're doing PCA first? Rotate.
The first part of PCA, yeah.
Okay. Here, the rotation might make sense because we are treating in this example here, I'm treating each dimension to be independent from each other. If they are not independent, instead of just computing variance, if I start computing covariance, then you're kind of learning. I'm not sure then if rotation will help, because then based on the density of the data, you should be able to compute the likelihood, and by rotation, the likelihood shouldn't change.
But the only reason I'm asking this question, because is if you have multivariate data that you're measuring with arbitrary instruments or arbitrary measures that you don't know that it's actually aligned appropriately, then you can't take that approach, right? Does it make sense? But otherwise, okay, anyway, I don't want to distract us too far, but I just the only concern that I had was that you don't, if you're using data that contains anomalies, as you said, and you're using the p-value to suggest what the percentages should be, you have a exaggerated variance to begin with.
I see what you're saying. Yes, kind of, because then the definition of anomaly is based on the variance, and based on the variance, you're saying that what percentage of your data is anomaly. So yes, but okay, but they're kind of using the same technique. They're saying that if here the only assumption here for us is, okay, that's the data, that's the normal distribution, dimensional independent from each other, and it's coming from maybe a normal Gaussian distribution. But sometimes you have extra assumption. It's like, I know for sure that 10% of the data is anomaly. If you add extra thing like that, then you can set that threshold based on your new assumption. Then you can maybe close it, or they call it like a contamination factor in most of the machine learning technique. They're saying that if you have any assumption about the data itself, then you can use it to find the best variance or the likelihood that will fit that percentage that you have in your mind. I'm not sure if I'm answering that.
You are, but again, the challenge is that if you say, okay, I have this distribution, and I want to take only the 1 out of 10,000, right? And you can go and get your cutoff for your p-value, right? But that's based off of the variance. Now, if you throw some highly anomalous extreme values in there, right? The variance that you have is not.
Yes.
Yes.
It means, okay, given a fixed data,
Yeah.
then you can compare, then if you have a percentage and a fixed data, but if you add data, if you change the distribution in any way, then the number will match, and then you can just use the same number again.
But if you winterize it, if you can appropriately remove extreme data without changing the central distributions, then you can get back the measure of variance spreads.
Yes.
Or whatever you want.
And the thing you're saying is a kinda like anomaly detection as well, but with different naming.
No.
It's like how they are doing that by removing extreme data. What is extreme data?
Well, it's just the rank ordered data.
It can be like that. So you remember in the video I was talking about the box plot. So it means if we have a bunch of data that are a bit far from the data percentage-wise or whatever, you can remove them. Usually in a statistical processing, they're removing those extreme data. And they're saying that I'm good, I'm fine with them, and I can do better things by just removing those extreme cases. But here, the task is if you are dealing with multi-dimensional data which are correlated to each other, how can you remove those things? What is the definition of extreme cases? And those extreme cases for us here will be anomaly. So yes. Okay, here we saw that what is the shape for anomaly. So we play with the threshold here, and we saw that the threshold will set different point to be anomaly or not if you change that p. If the p is super, like if your threshold is super small, then less amount of data will be categorized or detected as anomaly. If the threshold is super big, like even I can make it to be like a super big, and then see if it's like a too big, then you can say most of the data, everything is anomaly. So finding the best threshold is important. The other thing is the data is safe. Here the assumption was the data is normal, but not all the time it is normal, or it doesn't have just one peak. It can have actually two peaks in it. Here this data has two peaks. It's like maybe you're just dealing with the data that maybe, I don't know, if it's a price or if it's something, maybe the distribution of data is like mainly the data is, maybe if you're taking a price, most of the items are around $10 or around $100, and in between you don't have that much of data. So you can't just fit one normal distribution here, one Gaussian model here. And that's why if you have, let's say, two clusters in your data, then you will miss all the thing in between, because then the model will say, okay, everything in between is kind of part of the model. So maybe the average will happen actually here. So then anything happen here in between will be completely normal. So it means even here, if I make the threshold to be even lower, I mean higher actually, maybe too much. Let me make it to be like that. Still. See, then the only point that which is normal is the one in between, which is interesting because like, we are trying to find anomaly, and actually the point was normal, now is anomaly, and the one in between is normal, because I kind of increase the threshold too much. That's why just fitting one Gaussian or just computing standard deviation will give you a wrong number, wrong sample, if the assumption is wrong. So that's why I said in a statistic, sometimes you have in a statistical model here, sometimes you have assumption, sometimes you don't. Here you have assumption, and your assumption is the data is normal. Most of the time in machine learning, the assumption is everything is normal. If they want to do any regression model, anything, the assumption is normal. And based on having a normal distribution, they are doing lots of things, and not all the time the data is normal. So you can see that just fitting Gaussian work for just one normal distribution, but it won't work here because the data is completely different. See, even here, we won't cover that. And if you want to have a better, maybe, anomaly detection. See, now you're saying that, okay, all these points are anomaly, but we will completely ignore everything in the middle. And for the other one, which I guess was moon, same thing is happening. We are missing all the points in between. And if I lower that number again, change the number. See, we are covering more, but everything in the middle is normal. So if the data is a bit complex, just fitting a Gaussian can't help it at all. So that was kind of my lesson number 2 to start everything, is like the assumption of the data is important. Whenever we are talking about any kind of generative models, we have assumption usually. And the assumption is important because if you can verify the assumption using your data, then you will end up removing some extreme cases which they are not extreme, some rare event or some anomaly which they are not anomaly, or we will kind of ignore lots of points in the middle which they are kind of different from the actual data, but we will completely miss them because the assumption and the model can't capture those data at all. So I hope everyone has seen it in the code. Okay.